Hi guys, in this video we'll begin our look at the chemistry of epoxides. You should of course remember epoxide is the three-membered ring with one oxygen, two carbons. In this warm-up page here we see the biochemical synthesis of leukotrienes. The synthesis occurs in your body beginning with arachidonic acid and omega-6 fatty acid. And through different enzymatic conversions, one of the double bonds is converted to an epoxide here. We do have some chirality, two chiral carbons in this case. From there, different reactions of the epoxide reacts with cysteine and amino acid to give this leukotriene E4, it's known as. The epoxide here can also react with aqueous acid and to give another leukotriene. So reactions of epoxides, two example reactions of epoxides in these biochemical processes. And in the chemistry of epoxides, we'll first look at the synthesis. This should be review. You should have seen the synthesis of epoxides in Organic 1, typically from alkenes. And a common reagent to use is MCPBA, which is a peroxy acid. Of course, we have our group CO3. This is carbonyl O. If that was an H there, that'd be a carboxylic acid. But we have another oxygen and then the H. So CO3H, it's condensed down to. It is called a peroxy acid. Of course, if this was an HOOH, that would be hydrogen peroxide. The OO linkage is called a peroxide. This is considered a peroxy acid. The most common R group is the metachloro benzene ring to give metachloroperoxybenzoic acid. Okay, should be in your textbook. And the chlorine is meta. Now during test 2 we'll learn aromatic nomenclature and the positioning, relative positioning. If we start here, ortho, meta, para. So the chlorine's at the meta position, MCPBA. Okay, and dichloromethane here is shown as a common solvent. All right, you should review this reaction from your Organic 1. The alkene attacks, we have dipole here. And so the alkene attacks the electrophilic oxygen and kicks off the other. All right. I'm not going to go through this. Again, review your mechanism for epoxidation of an alkene. Here's your epoxide. Oxygen now bonded to the two carbons of the original alkene. In this case, one of the carbons is chiral, and we would expect a racemic mixture here. Here, the chiral carbon is indicated with a bond dashed bolded to oxygen. In this example down here, I show the oxygen-carbon bonds in the plane and the other groups either dashed or bold. We discussed this in Organic 1. Basically, this reaction is going to be stereospecific. And if you remember, if we can draw these two groups here, trans, okay, the ethyl and the methyl, but I told you we could draw these with stereochemistry already there. Okay. And then when we do the epoxidation, we know that the oxygen, the peroxy acid, comes from the top or the bottom. If it comes from the top, the new oxygen is going to be straight up. But we can keep these groups there just as in the original. Okay. Depends on the bond angle. It's back. I kind of drew it up. We could do that like that. And this one is forward. Those bond angles are a little ugly. But this would be this one. Okay. See how they're trans or trans? Better bond angle would be to show them kind of downward, but they're still back and forward. And then we would also have the oxygen straight down. And keep these the same. Keep one like that and keep one like that. Okay. If we call this A and B, this is B. This here is A. Okay, these two here are the same. If you take A and flip it, put the oxygen up, like my thumb now up, you'll see that these two groups, when you do that, this group will go back and that group will be forward. Okay. With the ring here, it's a little bit easier. You can consider this in the plane already. And it's very common to just put the oxygen forward or back. Ultimately, you should be able to handle the stereochemistry of the epoxidation when you bond the two carbons to the oxygen. All right. Another way to make epoxides is from halohydrins. If you remember, if we can take an alkene, react it with a halogen such as bromine or water, okay, we can get a halohydrin, vicinal halohydrin. If you take the halohydrin and treat it with sodium metal, you can get the epoxide. Because what does sodium do to an alcohol? Well, it's going to deprotonate it. Yeah, I don't like the word deprotonate. That sounds like an acid-base reaction. Remember, it's really a redox reaction. It will convert it to the oxygen anion. But then this will immediately come in here and do an internal SN2 and kick off the leaving group. All right. And we would get sodium bromide. The Br is the leaving group. The redox created the sodium ion. What else is generated here? If we started with the halohydrin, we would have also made hydrogen gas, right? But another way to make epoxides is from halohydrins, treating them with sodium metal or some type of strong base, strong enough to deprotonate the oxygen. Of course, the epoxide would be racemic. Racemic, the two enantiomers like shown above. Okay. sure there's likely some questions to come up here. I'm not going to go through every little possible detail. It depends on what questions you might have there. So that's the synthesis of epoxides. Reactions. First under acidic conditions. All right. Now, an epoxide is an ether. In the previous video and previous handout, we talked about reactions of ethers with acid. All right. Very similar. React this epoxide with HX. We have H plus and Br minus. Epoxide oxygen, we can protonate it. All right. And we have the same rule we showed on the previous handout. If we have a tertiary reaction site, we're going to go SN1. If no tertiary reaction site, we're going to go SN2. All right. But we also have another little rule here, which is sort of very odd. All right. That is that SN1 with epoxides actually gives inversion. Very strange. Okay. We do not have a tertiary site. We've got a secondary and a primary. So it's going to go SN2. If we're going to do SN2, we're going to attack which carbon? Which carbon? Top or bottom? Right or left? Well, it's going to be over here. Less substituted. Kick the oxygen off of that carbon. And that's going to give your product. It's going to be boom, boom, boom. The oxygen just leaves this carbon. It's still bonded over here and it's still fluoride. And now it's just a regular hydroxyl group. That was the leaving group. Now bonded to this carbon is the bromine. Now that carbon is not going to be chiral, so it doesn't matter if I draw it, how I draw it, just connect it there. Now I would typically do a zigzag. But there's your product upon reaction of that epoxide with HBr. All right. Well, let's try the next one. The only thing we can do is protonate the oxygen. I'm going to go ahead and do that. Okay. All right. Again, if you were on a quiz or test, you cannot skip steps like that, but we just protonated one above. I'm not going to go through the same type of step. All right, we have a tertiary carbon below and a secondary above. When a tertiary reaction site is present, always go SN1. So the oxygen is going to leave this carbon down here. Electrons, these bonding electrons move on to oxygen, and that's going to give, all right, this is still forward. It just leaves that carbon, but it's still forward. That was actually the leaving group that just left this carbon. There's a methyl down here. Now, before we start changing any of our previous knowledge or tweaking it a little bit, this would give this positive, and that carbon is now trigonal planar. All right, so the methyl group is no longer back, it's all in the plane. Now we have Cl minus, and we would attack there, and that would give our final product via an SN1 mechanism. Leaving group leaving, then nucleophile coming in. And we would typically say that it would become racemic down here. How do you attack a carbocation? From either side. But with epoxides, the leaving group only opens up a little bit. It's still very close. It doesn't ionize away and then move away. And these are electrons. Electrons are, they're close by. They're going to be attracted here. Okay? Gotta be careful. I'm not showing a bond here, I'm showing an IMF. That is, why would these electrons not sort of be here? It's kind of a partial bond. But that partial bond is going to be up because the oxygen is up. Because of that, the Cl minus does come in backside compared to, by the way, I call this back bonding. That leaving group is not going to move away and just ignore that cation. It will be back bonded a bit. And the back bonding takes place from the top because the oxygen is bonded up over here. That makes the chloride come in here. And the product here in terms of stereochemistry is, okay, when it comes in, it pushes this sort of IMF, this partial bond, fully away. The oxygen now is completely away from this carbon. The chlorine came in back, and that would push the methyl forward. So, it looks like we have inversion. But it wasn't SN2, because if it was SN2, the chloride should have attacked the top carbon and kicked the leaving group off. It's sort of a blended mechanism. It's SN1, but with inversion. Kind of crazy. It's something unique that happens with epoxides. We know it does. Can you imagine the first research student that observed this and went and told her professor? Said, yeah, I got inversion. And the professor's like, no. We know that SN1 gives racemic. And the student was like, well, somehow I got inversion. Well, we need to look at this. Nobody else has ever said epoxides give this. Somebody initially discovered this interesting or quirky chemistry of epoxides. Okay, there we go. Somewhat analogous to bromonium ion. Yeah, positive oxygen. Where would this attack? It would actually attack, remember in organic 1 we attacked here. Kick this off, but we called it backside. And that would have given bromine here, Cl here, and it would have moved the methyl forward. Okay? See, back in organic 1 with me, we covered this reaction before you even knew what an SN2 substitution was. This looks like SN2, but it's not, because if it was SN2, you should be attacking the top carbon because it's less substituted. But is it SN1? Well, if it was SN1, the leaving group should have left first, and you should have attacked a carbocation, and you should have got racemic. Well, really what happens is this bromine carbon bond sort of partially breaks, but it doesn't fully move away because physics tells us that electrons are going to remain attracted to that positive. Okay, it's a blended mechanism. What about other nucleophiles? Okay. Certainly possible. Here we use acid and halide X. What about acid and something else? Where here, sulfuric acid, we have H+, but what's the nucleophile? Well, it's never going to be the bisulfate anion. The nucleophile here is just water. We protonate the epoxide. Okay. And do we have a tertiary site available? No. So we're going to go SN2. A traditional SN2, the nucleophile attacks the less substituted carbon. Kick that off, and that's going to give boom, boom, boom. Oxygen just gets kicked off. It becomes OH. That was the leaving group. Now bonded to this carbon is the oxygen of water, but it has two H's. We don't just lose H's. These electrons may bond to carbon. That's what we just showed here. We need another step. We have H SO4 minus. That's what ionized to give us the H+. We could use this as the base to take the H. These electrons stay behind, and we would get that product there plus H2SO4 reformed. Okay, thus the sulfuric acid is a catalyst in this reaction. Ultimately, the epoxide just reacted with water, but was acid catalyzed. Now, the epoxide is not going to react with just pure water. We'll talk more about that. Weak nucleophiles require protonation of the epoxide. Okay, you might say, well, of course, or how else would the oxygen leave? Okay. And that's because we haven't said something down below yet. Okay. So think mechanistically. There's your product. The product is actually a diol. It's got two OH groups. Okay. You can just look and see it's a diol. It's not really anything to memorize. But this is important terminology. Try the next ones for homework. Okay. Sulfuric acid is aqueous. There is water here. But we have another nucleophile as well. Now, here you only really need one drop. Or even a micro drop, because the acid is actually catalyst. The methanol is going to be your nucleophile here. Yes, the one drop will contain a little water, but you're going to have so much more methanol. So when you see such like this, usually the other reactant is going to be your nucleophile and not the water. Okay. Now you can also try the mechanism below. All right. More complex mechanism. Now these are predictive product reactions, which sort of use our kind of sort of what I would call more straightforward. Okay, we have very specific thought process to predicting these products. Now with a mechanism, it could be a reaction that looks very strange. You're not asked to predict the product. You're asked to show the electron movement the mechanism for how this product is obtained, okay, and all the intermediates. All right. Please remember your mechanistic knowledge from Organic 1. And my guys, we had a handout that gave you some mechanism tidbits. Okay. General thoughts about mechanisms. So, here's a chance to practice that. It is epoxide chemistry, yeah? All right. Under acidic conditions. There's several statements we'll make in Organic 2. I haven't said this one yet. Typically, when you're under acidic conditions, the first thing you're going to do in a mechanism is protonate something. All right? Just a little advice, something to keep in mind. All right. Now, what about under basic conditions? All right. First off, I thought ethers were underreactive under basic conditions. We said that at the very end of the last handout. All right. That's true, but epoxides are different. Epoxides will react under basic conditions because of the ring strain. The small three-membered ring has ring strain. And it's very easy to open that ring up. And you actually do not have to have acid to make the oxygen leave. Okay? But you do need a strong nucleophile. Strong nucleophiles. We'll look at some examples, including Grignards. Okay? But first, let's look at acetylide anions. Our terminal alkyne, all right. Traditional base, sodamide it's called. These electrons take the H, these electrons stay behind. We get the acetylide anion plus ammonia, okay. You could also deprotonate with N-butyl lithium. I think we have seen this already in a previous handout. All right. To give the same product plus butane in that case. But the acetylide anion is a strong nucleophile. It's a carbanion. If we come in here with this epoxide, which by the way is the simplest epoxide you can have, okay, 2-carbon alkene converted to the 2-carbon epoxide, like with MCPBA. This is called ethene. The slang name for ethene is ethylene. And if you do a reaction with ethylene and then you determine that it seems to have an oxygen added to the molecule, okay, again, we draw structures on paper, but you know, in real life, you can't see structures in your flask. And 150 years ago, they didn't even know the structure hardly, but they knew atoms, and they knew that their original carbon-based compound had an oxygen added to it, and they called this ethylene oxide, which by the way is not an anion, so the "ide" ending is not appropriate. But in the end, I just wanted to let you know that the simplest epoxide is called ethylene oxide, and you sometimes see it used. It used to be used to sterilize surgical instruments. It's a gas. Okay, you can look it up if you'd like to know. In any event, there we go. And in this case, the nucleophile will attack one of the carbons and kick the oxygen off. First, which carbon will it attack? Well, if the epoxide is symmetrical, it doesn't matter. Both carbons are the same. All right? Let's attack this one and kick off the oxygen. Again, No H plus is required here. Okay? All right? Because of the ring strain. Looks very odd, don't it? How do you make oxygen a better leaving group? You protonate it. Or you put it in a compound that has ring strain, and it'll be willing to leave without being protonated if you have a strong nucleophile. And it will be SN2, and that is going to give this product here. Lone pairs, yeah? We just made this bond. Because the nucleophile is bonded to that carbon. Let's do it like this. Make sure you see it. There's the two carbons. When the oxygen leaves, it's going to be here. It will be minus now. Right? It takes on a third lone pair. The acetylide anion is bonded to this carbon. All right? Be careful with your triple bond. The triple bonded carbon is now bonded to that carbon, and then we have an R group. Well, that is this. These are the same thing. I just wanted to kind of redraw it so you can really see it. We just made this bond, this carbon-carbon bond. Now, something else we'll say many times with epoxides, the oxygen anion, carbon-carbon nucleophile. In all these reactions here, when the nucleophile attacks and opens up the epoxide, you're going to end up with nucleophile, carbon-carbon oxygen. Or in the final product, we'll say carbon-carbon OH. All right? Well, to get an H on the anion here, we can throw in either H+, or you can just throw in water. Water will work. Throw in some water, it will serve as a proton source, and we will protonate that, and there's your final product. That is a separate step. Okay? You cannot have water here because water will destroy your strong nucleophile. Separate step. We'll repeat this. And so you end up with, we just made this bond, nucleophile, carbon-carbon OH. This was your nucleophile, the R-acetylide anion. Okay? All right. I think I say that. All right. Let's look at Grignards next. All right. Alkyl anions. Now, removing the H from the alkyne is doable because of the acidity of the terminal alkyne. Regular alkanes are much less acidic, and it's much more difficult okay. And sort of a tricky way to make the alkyl anions is to start with the alkyl halide and react those with some type of metal, with the most common being group 1 metals. Okay? I'm sorry. Group 1 metals can be used, or group 2 metals. The most common is actually magnesium. But in this reaction, the metal will replace the halide, and the to give the Rm. Okay. If it's group 1. If it's group 2, you'll get RMX. All right. This is very generic. It's probably best to look at specific examples. All right. If you take an alkyl bromide reacted with lithium, a group 1 metal, all right, you will get an alkyl lithium. And we see the metal has replaced the halide, which is what we said up here. The halide is replaced with the metal. And we're also in this reaction going to make lithium bromide. That's the fate of the bromine. It becomes bromide. Now you do need 2 lithiums, so you need 2 equivalents of the lithium metal. With magnesium, which is group 2, you only need 1 equivalent, and the magnesium will replace the bromine. All right, but magnesium is 2+, and so the bromide will remain here to balance the 2+ charge of the magnesium. Now, both are essentially carbanions, because while this is drawn covalent, if we drew it ionic, it would be that and lithium plus. Okay. Now down here, if we drew this ionic, it would be that. Magnesium, we know ionically is 2+. And then you see that we need another minus. Well, the fate of the halide is to become the minus, and that balances everything out. But you see that what we form here in both cases is the carbanion. And it's much more easy and common to get to this by this reaction of the halide, the alkyl, or aryl. It can be aryl. We'll see more examples of this. Okay? It's actually a redox reaction. It's not a traditional acid-base reaction. I give you some information here, including that these cannot exist with an alcohol. All right? Very strongly basic. If you put these with an alcohol, these electrons will take an H, and you'll just protonate your alkane, alkyl anion. You'll just have an alkane or whatever. There. All right. I need to end the video here. Please do some reading, particularly about so-called Grignard reagents. That's when you use the magnesium. All right, it's the most common. More common than the alkyl lithiums. But now we can see reactions. Lithium, what does it do? Okay, well, we just showed that. Now, once you form these, this is a strong nucleophile, and if we come in with an epoxide, we can have a reaction. Appropriate workup. Appropriate workup is going to be very often water or H+. Okay? Now, since we have a strong nucleophile, the mechanism is always going to be SN2. Okay? You would only do SN1 when you have the H+ catalyst. strong nucleophile with epoxides, always SN2. All right. So do these for homework. Then here the halide, which can be iodine, okay, can be iodine, and it can be on an sp2 carbon. That's what we have here. Magnesium, THF is just a common solvent, okay. Okay, common solvents for making these reagents, making Grignard reagents, either diethyl ether or THF. All right. So we have alkyl lithiums or Grignards. We can then also use amines as strong bases. Now in this reaction we have a multi-step approach. All right. Please look at some of these for homework. We'll pick up here, and in the next video we'll also look at multi-step synthesis using epoxides as well as polymerization of epoxides. Okay guys, epoxide chemistry, very important, very interesting. It's got some nuances to it, some good mechanisms, and we're also introducing these reagents here, and the Grignard reagents in particular are hugely common, hugely important in organic chemistry. We'll use them more when we get to carbonyl chemistry in the second half of the course.